Welcome back, my friend. Most things around you look still, dark, and silent. But scientifically, every object in this room is glowing right now. Your hands, the walls, the floor, the chair, even the darkness around you is filled with invisible light. In this video, my friend, we're going to follow that hidden glow from ordinary objects to stars, to the afterglow of the Big Bang, and finally to the far future of a universe slowly fading into quiet. So for the next little while, let the day loosen its grip. You don't need to solve anything right now. Just settle in, breathe slowly, and let this quiet journey through invisible light carry your thoughts somewhere calmer. Chapter 1. The invisible light filling the room. One of the quietest and most surprising truths in physics is that the world around you is glowing all the time, and understanding why can make an ordinary room feel connected to the deepest behavior of the universe. Imagine sitting in a dark room late at night. The lamp is off. The window is black. The walls, the chair, the blanket, the book beside you, even your own hands may seem to have disappeared into shadow. To your eyes, the room has become almost empty. There is no visible light bouncing from the furniture into your vision, so the familiar shapes soften and fade. But physical reality has not gone quiet. The room is still active. Energy is still moving. Every surface is still sending out light. Just not the kind of light your eyes were built to see. That is the hidden idea at the center of this chapter. Objects do not need to be hot like fire to emit light. They only need to have temperature. A wall at ordinary room temperature, a cup left on a table, a pillow, a wooden shelf, a metal key, and the skin of your hand are all made of atoms and molecules in motion. Those tiny particles never sit perfectly still. They jiggle, rotate, vibrate, and exchange energy with one another. When matter has internal motion, it can release some of that energy as electromagnetic radiation. In everyday conditions, most of that radiation comes out as infrared light. Infrared light is real light. It belongs to the same broad family as the colors you see, the radio waves that carry signals, the microwaves that warm food, the ultraviolet light that can affect skin, and the X-rays used to see through the body. The difference is wavelength and energy. Human vision occupies only a narrow slice of the full electromagnetic spectrum. Our eyes are sensitive to the range we call visible light, because that range was useful for life under the sun. Infrared lies just beyond the red edge of vision. We do not see it directly, but we often feel its effects as warmth. This is why a dark room is not truly dark in every sense. It is dark to human eyes. To a thermal camera, the same room would look alive with gentle brightness. Your body would appear brighter than the cooler wall behind you. A warm mug might glow more strongly than the table beneath it. A window might reveal a different thermal pattern from the plaster around it. The shapes would be familiar, but the logic would be different. Instead of showing reflected visible light, it would show temperature, heat flow, and the quiet radiation leaving each surface. This invisible glow is not like the glow of a lamp. A lamp shines because electrical energy is being converted into visible light, either through a heated filament, a gas, or a semiconductor. A chair or a wall emits infrared light because its atoms are already carrying thermal energy. That radiation is usually too weak and too low in energy to appear as visible brightness. If an object is heated enough, however, the story changes. A piece of metal placed in a furnace begins to glow red, then orange, then yellowish white as its temperature rises. The glow shifts into the range our eyes can detect. The same basic principle is still at work, only the temperature has become high enough for the light to enter human vision. At ordinary temperatures, the glow remains hidden. This is why you do not look at your desk and see it shining. Your eyes are remarkable, but they are specialized instruments. They do not reveal everything that is present. They reveal what evolution shaped them to reveal. The room around you is full of electromagnetic activity, but most of it passes through your experience unnoticed. Reality is broader than sensation. There is always more happening than the body reports. The word radiation can sound alarming, but in physics, it simply means energy traveling outward. Light is radiation. Heat emitted as infrared is radiation. The warmth from a fireplace that reaches your face across a room is partly carried by infrared radiation. The energy arriving from the sun is radiation. The word does not automatically mean danger. Some forms of radiation carry enough energy to damage molecules inside living tissue, while infrared from ordinary objects is much gentler. It is part of the normal exchange of energy that surrounds life all the time. Every object in a room is both sending and receiving this invisible light. The wall emits infrared toward you, and you emit infrared toward the wall. The table emits radiation toward the floor, and the floor emits radiation back. A blanket radiates, absorbs, reflects, and slows the movement of heat. The room becomes a silent conversation of energy. Nothing has to move in a visible way for this exchange to happen. Even in still air, even in darkness, surfaces are continually sharing thermal radiation. This helps explain why temperature is not just a number on a thermometer. It is connected to motion inside matter and to the way matter communicates with its surroundings. A warm object is not storing heat as a mysterious fluid. It is holding energy in the motion and arrangement of its particles. Some of that energy can move into nearby objects by contact. Some can be carried by moving air. Some can travel away as infrared light. Radiation is special because it does not require touch or air. It can cross empty space. That point is what links your room to the universe. The same kind of energy transfer that lets your skin radiate warmth into the air also allows planets to shed heat into space. Earth absorbs visible and ultraviolet light from the sun, warms up, and then releases much of that energy back outward as infrared radiation. The balance between incoming sunlight and outgoing infrared is central to the planet's climate. A planet is not just a rock under a star. It is a body continually exchanging light with space. A room at night is a small version of a much larger truth. Matter with temperature glows. Cool matter glows mostly in longer, invisible wavelengths. Hotter matter glows in shorter wavelengths and may become visible. Stars shine because their outer layers are extremely hot, so a large part of their radiation pours out in visible light. Cooler objects such as planets, moons, dust clouds, and human bodies still glow, but mostly in infrared. Nothing needs to be alive to do this. Nothing needs to be burning. A silent stone, if it has temperature, participates in the same physical process. This idea changes the feeling of darkness. Darkness is often treated as absence, as though the lights go out and nothing remains. But scientifically, darkness can simply mean that the available light is outside the range your eyes can detect. A bedroom after midnight is not empty of light. It is full of infrared light. The world is not failing to shine. You are only missing the part of its shining that your eyes cannot receive. Thermal cameras make this hidden layer visible by translating infrared radiation into colors or brightness that humans can interpret. They do not create the glow, they reveal it. In their images, footprints can linger on a floor for a short time because the floor surface has been warmed by contact. A handprint may remain on a wall after the hand is removed. Warm pipes may show through a surface. Heat leaks around a window can become visible. These images can feel strange because they show a world that was always there, moving underneath ordinary sight. Yet the physics is gentle and exact. Atoms and molecules carry energy. Their motion affects how matter emits radiation. Warmer things usually emit more radiation than cooler things. The details depend on the material, the surface, and how well it absorbs or emits certain wavelengths. But the central idea remains simple. Temperature leaves a kind of light signature. Every object carries a quiet announcement of its thermal state. This is also why no ordinary object can be perfectly hidden from the universe if it has temperature. It may be dark to the eye, it may be silent to the ear, it may sit motionless on a shelf. Still, it is radiating. In a deep scientific sense, it is communicating with its surroundings. Its presence is written into the field of light around it. The signal may be faint, but faint does not mean unreal. There is something humbling about this. The room you are in may seem still, but it is filled with exchange. Your body is part of it. The walls are part of it. The ceiling, the floor, the glass in the window, your clothes, the device playing this video, all of them are glowing quietly. You are not separate from this invisible field. You are one warm object among many, giving and receiving energy, connected to the physics of planets, stars, and the early universe. And this is where the subject becomes larger than a room. If every object around you glows because it has temperature, then the universe itself can be understood partly through glow. Astronomers study visible light from stars, infrared light from dust, microwave light from ancient cosmic radiation, and many other wavelengths that the human eye could never see. The cosmos is not only something we look at, it is something we learn to translate. Each kind of light tells a different story about temperature, motion, matter, and time. So tonight, when the room becomes dark, it may help to imagine that darkness differently. Around you, the hidden light is still flowing. Your body is softly giving warmth to the space around it. The objects nearby are quietly returning their own invisible glow. Nothing needs to be forced. Nothing needs to be solved right now. The day can loosen its grip, and you can rest inside a universe that is still gently shining, even when your eyes are closed. Chapter 2. Why warm things emit light. Warmth may feel like a private property of an object, something held quietly inside a hand, a stone, or a cup of tea. But in physics, warmth is never completely silent. Whenever matter has temperature, it carries energy in the motion of its particles, and some of that energy is continually leaving as light. To understand why, it helps to begin with matter itself. A solid object may look perfectly still on the outside, but inside it is restless. Its atoms are held in place by electrical forces, almost like tiny weights connected by invisible springs. They cannot usually wander freely through the object, but they can vibrate around their positions. In a liquid, the particles slide and tumble past one another. In a gas, they fly freely until they collide. In every case, temperature is connected to this microscopic motion. A warmer object has, on average, more internal motion than a cooler one. That motion matters because atoms are built from charged particles. The tiny electrons around atoms carry electric charge, and the nuclei at the centers of atoms carry positive charge. Whenever charged particles shift, vibrate, or are disturbed by nearby particles, the surrounding electromagnetic field is disturbed as well. Those disturbances can travel outward as electromagnetic waves. Light is one form of electromagnetic wave. So, when matter is warm and its charged parts are constantly moving, the matter has a natural way to send energy outward as radiation. This does not mean that each atom is shining like a miniature lamp in a simple visible way. The process is more subtle. Inside ordinary matter, particles interact constantly. They exchange energy. They collide, vibrate, and settle into patterns allowed by quantum physics. Energy can be absorbed and released in small packets. Across a huge number of particles, these tiny events blend together into a steady thermal glow. The result is not a single color or a single kind of light. It is a spread of wavelengths, with some emitted more strongly than others. The temperature of an object decides where most of that radiation appears. At everyday temperatures, the strongest part of the glow lies in infrared light. That is why a human body, warm water, furniture, clothing, and walls do not usually appear visibly bright. Their thermal radiation is mostly beyond the red edge of human vision. If an object becomes much hotter, the pattern shifts. A heated stove coil may begin to glow dull red. Hot metal in a forge may shine orange, yellow, or almost white as its temperature rises. The object has not gained a magical new property. The same thermal process has moved into wavelengths the eye can detect. This shift is one of the most important clues in the science of heat and light. Cooler objects emit longer wavelength radiation. Hotter objects emit more radiation overall, and a larger share of it appears at shorter wavelengths. That is why color can reveal temperature. A red-hot object is cooler than a white-hot object. A blue-white star is hotter at its visible surface than a red star. The connection is so reliable that light becomes a thermometer across distance. By reading the color and spectrum of radiation, scientists can learn the temperature of objects they will never touch. There is a common misunderstanding here. People often think objects glow because they are burning. Burning can certainly make things hot enough to glow, but burning is a chemical reaction, while thermal radiation is more general. A stone warmed by sunlight radiates. A planet radiates. A person radiates. A star radiates from its hot outer layers. A piece of metal inside a furnace radiates even if it is not chemically burning away. The deeper rule is temperature. If matter has temperature, it emits electromagnetic radiation. The ideal version of this behavior is called black body radiation. The name can sound strange because it does not mean the object must look black in ordinary life. A black body is a theoretical object that absorbs incoming radiation perfectly and emits thermal radiation in a way determined only by its temperature. Real objects are more complicated. Some surfaces emit infrared efficiently, others reflect more. Polished metal behaves differently from dark cloth. Skin behaves differently from glass. Yet, the black body idea remains powerful because it reveals the underlying pattern behind thermal glow. A perfect black body would be like the cleanest possible example of temperature turning into light. At a given temperature, it produces a smooth range of wavelengths, with a peak that depends on how hot it is. Real materials may have extra details in their spectra because of their structure and chemistry, but the broad rule still guides the story. Temperature shapes the radiation. Surface properties adjust how strongly and in what way the radiation escapes. This is also why objects are constantly balancing absorption and emission. A warm object is losing energy as radiation, but it may also be receiving radiation from everything around it. If it receives as much energy as it emits, its temperature can remain steady. If it emits more than it receives, it cools. If it absorbs more than it loses, it warms. Heat is therefore not locked inside objects. It is always moving through contact, through flowing fluids such as air or water, and through radiation. Radiation is especially important because it can move through empty space. Conduction needs direct contact. Convection needs moving material. Radiation only needs the electromagnetic field. This is why sunlight can cross the emptiness between the sun and Earth. It is also why Earth can lose heat back into space. On a smaller scale, it is why you can feel warmth from a fire before touching anything hot. Your skin absorbs some of the infrared radiation arriving from the flame and surrounding hot surfaces. The amount of radiation rises very strongly with temperature. A small increase in temperature can make a significant difference in emitted energy. This is why hot objects can feel intense from a distance, while objects only slightly warmer than their surroundings may be difficult to notice without instruments. It is also why glowing metal changes so dramatically as it heats. The internal motion becomes more energetic, the electromagnetic disturbances become stronger, and the emitted light increases across a wider range of wavelengths. At the microscopic level, heat is messy but not meaningless. The particles inside matter do not all move with the same energy at the same moment. Some are more energetic, some less. Energy is constantly passed around. Over time, a stable pattern emerges that matches the temperature of the material. Thermal radiation is the outward sign of that internal statistical order. It is the visible or invisible trace of countless microscopic motions averaged into one smooth behavior. Quantum physics adds another important layer. Atoms and molecules cannot always absorb or release energy in any amount they please. Many processes happen in discrete steps. Electrons, vibrations, and rotations have allowed energy states. In gases, these energy steps can create sharp lines at particular wavelengths. In dense solids and liquids, interactions among many particles broaden the behavior into a more continuous glow. That is part of why a hot solid can shine with a smooth color, while a thin gas may give off light in more specific wavelengths. This difference helps connect everyday objects to astronomy. Stars, gas clouds, planets, and dust all reveal themselves through the radiation they emit or absorb. A star's dense visible surface behaves somewhat like a thermal radiator, producing a broad spectrum shaped by temperature. Cooler cosmic dust glows strongly in infrared. Thin clouds of gas can add or remove narrow features from the light passing through them. By studying these patterns, scientists can learn temperature, composition, motion, and density across enormous distances. The simple act of warming something is therefore connected to one of the main ways the universe becomes knowable. A kettle, a stone, a candle flame, a planet, and a star all belong to the same larger language of heat and radiation. They differ in temperature, size, material, and environment, but they all show how energy inside matter can become light moving outward. There is beauty in the fact that this process is automatic. An object does not choose to glow. It does not need to be observed by a person. The radiation happens because of the physical state of the matter itself. As long as the particles have energy, as long as the object has temperature of absolute zero, the electromagnetic field carries some of that energy away. Absolute zero would represent the lowest possible thermal state, a limit where ordinary thermal motion is minimized as far as nature allows. Real objects never casually reach that limit. In the world we live in, everything has some thermal presence. This also means that light is more than what allows sight. Light is one of the ways matter shares energy with the rest of reality. The warmth leaving your hand, the glow of a coal, the light of a star, and the faint radiation from a distant planet are all variations on this same theme. They are messages written in wavelength and intensity. Some messages are bright enough for the eye, others require instruments, but each one tells us that matter is active inside. So when you think of a warm object, you can imagine more than surface comfort. You can imagine a hidden motion, a field responding, an energy leaving in waves too long for your eyes to catch. The object is quietly translating temperature into light. It is doing what matter has done since the early universe cooled enough for atoms to form, and what matter will continue doing for as long as there is warmth left to release. And as the day settles, this thought can become peaceful rather than overwhelming. The warmth around you is not noise. It is a gentle exchange, a soft physical conversation between your body and the world nearby. You can let that quiet glow surround you and allow the evening to become slower, softer, and easier to leave behind. Chapter 3. The Spectrum Beyond Human Eyes. Human sight feels complete because it gives the world shape, color, distance, and movement. Yet the colors we see are only a narrow opening in a much wider sea of light. When you look at a room, your eyes seem to tell you what is there. They show the edge of a table, the pale surface of a wall, the dark line of a doorway, the color of fabric, the small reflection on glass. Vision feels immediate and trustworthy because it is the sense humans rely on so deeply. But sight is selective. It gathers only a small range of electromagnetic radiation and leaves the rest untouched. The world is constantly crossed by forms of light that never become color in the human mind. All electromagnetic radiation is related. Radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays are not separate substances. They are different regions of one continuous spectrum. The difference between them comes mainly from wavelength and energy. Long wavelengths carry less energy per photon, while shorter wavelengths carry more. Human eyes evolved to detect a thin middle region, the part we call visible light. Within that small region, the brain builds the colors of the familiar world. A rainbow gives a simple glimpse of this arrangement. When sunlight passes through water droplets or a prism, the visible part spreads into red, orange, yellow, green, blue, and violet. Those colors appear separate to us, but they are neighboring parts of a smooth range. Red light has a longer wavelength than violet light. Beyond red lies infrared, which human eyes do not see. Beyond violet lies ultraviolet, which is also hidden from direct vision. The rainbow is beautiful, but it is also incomplete. It is only the visible slice of a much larger structure. This matters because every region of the spectrum interacts with matter in its own way. Radio waves can travel across great distances and pass through many materials that block visible light. Microwaves can interact strongly with certain molecules, especially water in a kitchen oven. Infrared is closely connected to warmth and thermal emission. Visible light reflects from many surfaces in ways that let eyes and cameras form images. Ultraviolet carries more energy and can drive chemical changes. X-rays can pass through soft tissue more easily than dense bone, which is why they can reveal internal structure. Gamma rays carry even higher energy and are often linked with the most violent processes in nature. The names make the spectrum feel divided into separate categories, but the borders are human labels. Nature does not draw a hard line where red ends and infrared begins, or where ultraviolet becomes X-rays. Scientists use these names because they are useful. They describe how radiation tends to behave, how it is produced, how it is detected, and how it interacts with matter. The spectrum is continuous, while our vocabulary divides it into regions so the mind can handle it more easily. The human eye is tuned to visible light partly because of the sun. The sun sends out a wide range of radiation, but a large amount of its energy reaches Earth in and near the visible range. Earth's atmosphere also allows much visible light to pass through to the surface. For living organisms on the ground, this made visible light an especially valuable source of information. Eyes that could detect it helped animals find food, avoid danger, move through space, and recognize patterns. Human vision is not a complete scientific instrument. It is a biological solution to living under a particular star, behind a particular atmosphere, on a particular planet. Other creatures experience the spectrum differently. Some insects can detect ultraviolet patterns on flowers that humans cannot see. Some snakes can sense infrared radiation from warm animals, giving them a kind of thermal awareness. Many birds see a wider range of color than humans, with visual systems that include sensitivity beyond our ordinary limits. These abilities remind us that the visible world is not the same for every living thing. What appears plain to one species may be marked bright or meaningful to another. Technology extends human perception much further. A radio antenna can receive long wavelength signals that eyes could never notice. An infrared camera can reveal warm surfaces in darkness. Ultraviolet instruments can show patterns in materials, atmospheres, and stars. X-ray detectors can reveal energetic regions around compact objects in space. Gamma-ray observatories can detect some of the most powerful events in the universe. Each instrument does something similar to what the eye does, but in a different part of the spectrum. It receives radiation, converts it into a signal, and allows the brain to interpret that signal through an image, a graph, or a measurement. This is why many scientific images are translated into visible colors. When you see a picture of a nebula glowing in deep red, blue, green, or gold, those colors may not always represent what your eyes would see from nearby. Sometimes they show wavelengths that are invisible to human vision. Scientists assign visible colors to different kinds of radiation, so the hidden structure becomes readable. A region that emits infrared may be given one color. A region that emits X-rays may be given another. The result is not fake in the sense of being invented. It is a translation, a way of bringing invisible information into human perception. Astronomy depends on this translation. For most of human history, the universe was studied mainly through visible light. People watched the sun, moon, planets, and stars with their eyes, then with lenses and mirrors that gathered more visible light. This revealed an enormous amount. Yet once astronomers learned to observe other wavelengths, the universe changed. Radio astronomy revealed cold hydrogen gas, pulsars, and giant structures invisible to ordinary telescopes. Infrared astronomy opened views through dust that blocks visible light, showing hidden star-forming regions. Ultraviolet observations revealed hot young stars and energetic gas. X-rays exposed violent environments around black holes, neutron stars, and superheated matter. Gamma rays pointed toward explosions and extreme particle processes. The same object can look very different depending on the wavelength used to observe it. A galaxy in visible light may show stars and dark lanes of dust. In infrared, some of that dust becomes less of a barrier and cooler material begins to glow. In radio waves, the same galaxy may reveal gas, magnetic fields, or energetic jets. In X-rays, it may show hot gas or a powerful center. No single wavelength gives the whole truth. Each one gives a layer. To understand the universe, scientists combine those layers into a richer picture. This idea also applies close to home. A wall seen in visible light gives information about color, texture, and shadow. In infrared, it may reveal temperature differences. In radio waves, it may be partly transparent depending on the material and wavelength. Under ultraviolet light, certain substances may fluoresce. The object has not changed. The method of seeing has changed. A surface is more than the appearance it offers to human eyes. The spectrum teaches a quiet lesson about perception. The world does not become real only when we can see it directly. Much of reality is present outside ordinary awareness. Human senses are useful, but they are limited by biology. Instruments do not replace wonder. They widen it. They show that familiar objects contain more information than vision alone can gather, and that the universe has been speaking in many forms of light long before humans learned to listen. Even darkness becomes more interesting through this view. A place can be dark in visible light and bright in infrared. A cloud of dust can hide newborn stars from ordinary vision while glowing at longer wavelengths. Empty-looking space can contain radio emission, microwave background radiation, ultraviolet light from hot stars, and high-energy signals from extreme events. The eye sees absence where another instrument may see activity. Darkness is sometimes a statement about the observer, rather than a statement about the world. There is also a deep connection between wavelength and scale. Long radio waves can be comparable to buildings, mountains, or even larger structures depending on the signal. Visible wavelengths are tiny compared with everyday objects, which is why they can reveal fine surfaces and edges to our eyes. X-rays and gamma rays have much shorter wavelengths, allowing them to interact with matter in ways tied to atoms, nuclei, and high-energy processes. Across the spectrum, light becomes a measuring tool, a messenger shaped by the size and energy of the things that produced it. This is why the phrase light deserves to feel larger than color. Light is information traveling through space. Sometimes it arrives as red sunlight through a window. Sometimes it arrives as radio waves from a distant cloud of gas. Sometimes it arrives as infrared from a warm body, ultraviolet from a hot star, or X-rays from matter heated to extraordinary temperatures near a compact object. Human eyes receive one small chapter of that story. Science learns to read the rest. For this video, that wider idea is essential. If every object around you is glowing, then the reason you do not see that glow is not that it is unreal. It is simply written in a part of the spectrum your eyes cannot read. The invisible glow of a room belongs to the same grand family as starlight, radio signals, ultraviolet radiation, and the ancient microwave light that fills the universe. Once you understand the spectrum, the world no longer feels like a place divided into light and darkness. It feels like a place filled with messages, most of them quiet, waiting for the right way of seeing. And as you settle into the night, this can be a calming thought. There is no need to hold the whole spectrum in your mind at once. It is enough to know that reality is wider than the day made it feel, and that even in darkness, the universe remains softly present around you. Chapter 4. Your body as a quiet source of radiation. Your own body is one of the most familiar examples of the hidden glow described in this video, because even while you are resting, breathing slowly and sitting perfectly still, you are releasing invisible light into the space around you. This may sound strange at first because the body does not feel like a shining object. You do not look at your hand in a dark room and see it lighting the wall. You do not see a soft outline of brightness around your skin. To ordinary vision, a person disappears when visible light disappears. But the body is warm, and warmth has a physical signature. The skin, the blood beneath it, the muscles, the organs, and the living cells inside you are all part of a system that produces, carries, and releases heat. Some of that heat leaves as infrared radiation. The source of this warmth is life itself. Every cell in the body needs energy to keep working. Cells use energy to build molecules, repair damage, move substances, send signals, maintain internal conditions, and power muscles. Much of the energy used in these processes eventually becomes heat. Even when you are lying still, your body is active. The heart continues to beat. The brain continues to process signals. The liver, kidneys, lungs, and digestive system continue their quiet work. Life is never a frozen state. It is controlled motion, and controlled motion produces heat. The body works hard to keep its internal temperature within a narrow, safe range. Deep inside, around the organs and brain, temperature is held far more steadily than the temperature of the surrounding air. This stable internal warmth allows enzymes and cells to function properly. If the body becomes too hot or too cold, important chemical processes begin to struggle. So the body constantly adjusts how much heat it keeps and how much heat it releases. The skin is the main boundary where this exchange happens. It is a living surface with blood vessels, sweat glands, nerves, and layers that help regulate heat. When the body needs to release more warmth, blood vessels near the skin can widen. More warm blood flows close to the surface, and the skin becomes a better path for heat to leave. When the body needs to conserve warmth, those vessels can narrow. Less warm blood reaches the surface and heat loss slows. This is why skin can flush when you are warm and become paler or cooler in the cold. Infrared radiation is one of the ways the skin releases energy. The surface of the body emits invisible light because it has temperature. The radiation does not need air to carry it, and it does not need direct contact with another object. It moves outward as electromagnetic energy. Nearby walls, clothing, blankets, and furniture are also emitting and absorbing radiation, so your body is always part of a quiet exchange with its surroundings. This exchange depends on the difference between your skin and the environment. In a cool room, your body usually radiates more energy outward than it receives back from the cooler surfaces around it. That is one reason a cool room can slowly draw warmth from you, even when the air is still. In a warm room, the balance changes. If the surrounding surfaces are close to skin temperature, radiation becomes less effective as a cooling pathway. If the surroundings are hotter than your skin, your body can even gain radiant heat from them. This is why shade matters on a hot day. It reduces the amount of radiation your body receives from direct sunlight and heated surfaces. The body has other ways of losing heat as well. Heat can move by direct contact when your skin touches a cold surface. It can be carried away by moving air. It can leave through evaporation when sweat turns into vapor. These pathways work together, and the balance changes with temperature, humidity, clothing, wind, activity, and health. During quiet rest in comfortable conditions, radiation can be a major root of heat loss. During heavy exercise or hot weather, sweating and evaporation become especially important. The body does not depend on one method alone. It adjusts through several overlapping systems. A thermal camera makes this hidden process visible by sensing infrared radiation from the surface of the body and translating it into a visible image. The warmest areas often appear brighter or more intense in the image, depending on the color scale chosen. The face, neck, hands, and areas with strong blood flow can stand out. Covered areas may appear different because clothing changes the way heat reaches the outside surface. A thick coat does not stop the body from producing heat, but it changes how that heat escapes and how much infrared radiation comes from the outer surface seen by the camera. This is why thermal images are not simple pictures of the body's inner temperature. They mostly show surface temperature and emitted infrared radiation from whatever surface is exposed. A thermal camera looking at a person sees skin, hair, clothing, glasses, and the effects of the surrounding environment. Wet skin, airflow, reflective materials, and recent contact with warmer or cooler objects can all change the image. The body is a living heat source, but the picture of that heat is shaped by many surface details. Still, the basic fact remains remarkable. Your body can be detected in darkness because it emits infrared light. A person walking through a dark landscape may be nearly invisible to ordinary eyes, yet visible to a thermal sensor. A hand held near a cool wall may leave behind a temporary warmer patch. Feet may warm the floor. A face may glow softly in infrared against a cooler background. These effects reveal that the body is always leaving thermal traces, small signs of the energy moving through living tissue. There is a poetic temptation to imagine this as a kind of aura, but the scientific reality is more grounded and more interesting. The body's glow is a measurable result of temperature, metabolism, circulation, and the behavior of electromagnetic radiation. It does not require belief. It does not depend on imagination. It is part of the same physics that lets a warm stone cool under the night sky and lets Earth release absorbed sunlight back into space. The amount of radiation your body emits changes slightly through the day. Physical activity raises heat production. A warm meal can alter metabolism for a time. Sleep changes circulation and temperature regulation. Illness can raise internal temperature and shift the pattern of heat leaving the skin. Emotions can also affect circulation in visible ways, such as warmth in the face or hands, because the nervous system can change blood flow. The infrared body is a living map of regulation, movement, and exchange. Even breathing is connected to heat. Air enters the nose or mouth, is warmed and moistened inside the body, and leaves carrying heat and water vapor. In cold air, breath becomes visible because water vapor condenses into tiny droplets. But the heat was present even before the cloud appeared. The visible mist is only one sign of a larger exchange. The body is constantly giving some of its energy to the environment, then replacing that energy through metabolism. Clothing changes the story in a practical way. A sweater or blanket does not create warmth from nothing. It slows the loss of heat. It traps air, reduces convection, and places layers between your warm skin and cooler surroundings. The outer surface of the fabric may become much cooler than your skin, so it emits less radiation outward than exposed skin would. At the same time, the inner layers help reflect and absorb some thermal energy near the body. This is why insulation feels comforting. It changes where and how the glow escapes. Your skin also has properties that make it an efficient emitter of infrared radiation. Human skin, across much of the thermal infrared range, behaves more like a strong emitter than a shiny reflector. This is one reason thermal cameras can detect people well. Polished metal can confuse thermal readings because it reflects infrared from the environment, but skin tends to send out its own thermal signal clearly. Materials matter. Surface texture, moisture, and composition all affect how radiation is emitted and absorbed. The body's infrared glow is also part of why living things are visible to some animals in ways humans are not. Certain snakes can detect infrared radiation from warm prey through specialized sensing organs. They are not seeing the world exactly as a thermal camera does, but they are using heat-related radiation as information. For them, warmth can help reveal the presence of another animal. Human beings built instruments to do something similar, extending perception beyond the limits of the eye. All of this can make the body feel less separate from physics. The warmth of your hands, the comfort of a blanket, the coolness of a window at night, and the feeling of stepping into shade are everyday experiences of energy transfer. The body is made possible by the laws of matter. It manages heat carefully because life depends on balance. It emits radiation because warm matter does. It becomes visible in infrared because biology and physics meet at the surface of the skin. There is also a quiet humility in knowing that the body is always giving energy away. We often imagine ourselves as closed individuals, sealed inside our skin, but physically we are open systems. We take in energy from food and oxygen. We release heat, breath, moisture, and motion. We exchange radiation with the room. We are constantly connected to our surroundings in ways too subtle for sight to notice. So as you rest, your body is still working gently on your behalf. It is holding its inner warmth, releasing what it does not need, and keeping balance without asking for attention. The invisible glow around you is part of that quiet care. Let the thought become soft. Let the day settle. Your body knows how to continue its steady work while you loosen your grip on everything else. Chapter 5. The Hidden Temperature of Objects. Temperature is one of the most familiar ideas in daily life, yet the way objects feel to the hand can be deeply misleading because your skin does not measure temperature alone. It measures the movement of heat. Touch a metal spoon lying on a kitchen table, and it may feel cool. Touch a wooden handle in the same room, and it may feel warmer. The natural guess is that the spoon has a lower temperature than the wood. Very often, that guess is wrong. If both objects have been resting in the same room for long enough, they may be close to the same temperature. The difference is in how quickly they move heat away from your skin. Metal is a good thermal conductor. It accepts energy from your hand rapidly, so your skin loses heat quickly, and your nerves report the feeling as cold. Wood is a poorer conductor. It takes heat from your hand more slowly, so it feels warmer even when its actual temperature is similar. This small experience reveals something important. The body does not sense temperature the way a scientific instrument does. It senses change. Your skin contains nerve endings that respond to warming and cooling. They tell the brain whether heat is entering or leaving the skin, and how quickly that transfer is happening. This is why a surface can feel cold without being much colder than its surroundings, and why a surface can feel warm because it is slowing the loss of your own heat. The hidden temperature of objects is therefore partly hidden by perception. Your hand is useful for survival, but it is not a precise thermometer. It evolved to warn you about dangerous heat, damaging cold, and changes in contact with the environment. It was never meant to reveal the exact thermal state of a table, a stone, a window, or a piece of cloth. The sensation is real, but it is an interpretation shaped by the movement of energy between your skin and the material you touch. Different materials handle heat in different ways. Thermal conductivity describes how easily heat moves through a substance. Metals usually conduct heat well because their internal structure allows energy to move efficiently through vibrations and mobile electrons. This is why metal pans carry heat from a stove into food, and why metal tools left outside in winter can feel painfully cold. Wood, plastic, cloth, and still air conduct heat much less effectively. They slow the transfer, which is why they often feel gentler to touch. There is another property that matters: heat capacity. This describes how much energy a material needs in order to change temperature. Water has a high heat capacity, which is why oceans warm and cool slowly compared with land. A pot of water can store a large amount of heat without its temperature rising as quickly as a smaller or less heat-holding material might. Stone, metal, air, fabric, and glass all store and release heat differently. The temperature you feel depends on both how much energy is present and how quickly that energy can move. A blanket is a good example of this hidden logic. A blanket does not create heat by itself in ordinary use. It feels warm because it slows the escape of heat from your body. It traps layers of air, and still air is a poor conductor. The fabric also reduces air movement near your skin, so less warmth is carried away. When you slip under a blanket, the space around your body gradually warms because your own heat is being kept close. The blanket becomes warm through exchange with you, not because it began as a source of energy. This is why a blanket left alone in a cold room is not truly warm. It may feel less cold than a metal object in that room, but that is because it pulls heat from your hands slowly. Once your body is under it, the blanket becomes part of a small thermal environment. It turns your own warmth into comfort by slowing its escape. In that sense, much of what we call warmth in daily life is really the protection of warmth already present. Glass gives another interesting example. A window pane on a winter night may feel cold because it is connected to the colder outside environment and can lose heat quickly through its surface and structure. Your hand touching it sends heat into the glass, and the glass passes energy onward. Yet glass is not as conductive as metal, so it does not behave exactly like a metal rail or spoon. Its cold feeling also depends on thickness, air movement, coatings, and the temperature difference between inside and outside. A simple window can become a quiet map of heat escaping from a building. Objects in sunlight reveal another layer. A dark stone lying under the sun may become much warmer than a pale stone nearby because darker surfaces often absorb more visible light. A black shirt can heat up more quickly than a white one in strong sunlight. The color that your eyes see is connected to how the material handles visible light. although the full story also includes infrared absorption and emission. Surfaces that absorb energy well can warm, and surfaces that emit energy well can cool efficiently under the right conditions. Color, texture, material, and environment all shape an object's hidden temperature. This is especially noticeable outdoors after sunset. During the day, pavement, brick, soil, and stone absorb sunlight and store energy. After the sun goes down, they continue releasing that heat. A city street can remain warm long after the air begins to cool. A large rock may hold warmth into the evening. Sand may change temperature quickly near the surface while deeper layers remain different. The world is full of delayed thermal memory. Objects remember earlier sunlight in the form of stored heat, then slowly give that energy back. The same idea appears on planetary scales. The moon, with little atmosphere to spread heat around, can have extreme surface temperature differences between sunlight and shadow. Earth's oceans store heat and release it slowly, helping moderate climate. Deserts can become very hot during the day and cool rapidly at night because dry air and exposed surfaces do not hold and redistribute heat the way water-rich environments do. The hidden temperature of objects is not only a household subject. It helps explain landscapes, weather, and the behavior of worlds. Radiation adds another quiet layer to the story. Every surface with temperature emits thermal radiation, but surfaces differ in how efficiently they do it. This property is called emissivity. A dull, dark surface often emits infrared radiation efficiently, while a shiny metal surface may reflect much of the infrared radiation around it and emit less effectively. This is why reflective emergency blankets can reduce heat loss. They reflect some thermal radiation back toward the body and slow the escape of warmth. Again, the feeling of temperature depends on more than the temperature itself. In everyday life, heat is always trying to move from warmer regions toward cooler ones. A hot drink cools because energy leaves it through the cup, the air, evaporation, and radiation. Ice melts because energy from the surroundings enters it. A room becomes more comfortable when heating, insulation, airflow, and surfaces reach a balance. The hidden temperature of an object is therefore not isolated. It belongs to a network of exchanges. This is why two rooms at the same air temperature can feel different. A room with cold walls and a cold floor may draw radiant heat from your body, making you feel cooler, even if the air itself seems acceptable. A room with warm surfaces can feel comfortable at a lower air temperature because your body loses less radiant heat to the surroundings. Comfort is not just air temperature. It is the whole thermal environment around you. Even the simple act of placing your hand on a table creates a temporary thermal event. Your skin warms the surface slightly. The material carries that warmth inward or holds it near the surface depending on its properties. When you lift your hand away, the warmed patch begins to fade as the energy spreads and leaves. Most of the time, you cannot see this trace, but it is there. Your contact has briefly changed the object's thermal state. The hidden temperature of objects teaches us that the world is less still than it appears. Furniture, walls, floors, clothing, stones, water, and glass are all storing, moving, absorbing, and releasing energy. Some materials share heat quickly, some resist it, some hold energy for a long time, some lose it easily to the air or sky. The ordinary room becomes a slow, invisible landscape of thermal motion. This is a gentler way to understand the phrase, "everything is glowing." The glow is only one part of a wider exchange. Objects do not merely sit in space with fixed temperatures. They are constantly adjusting to contact, light, air, shadow, and the surfaces around them. Their temperature is a history of where they have been, what they have touched, what light they have absorbed, and how easily they can let energy go. So when you feel the coolness of a window, the softness of a blanket, or the warmth of a cup in your hands, you are touching a flow rather than a fixed thing. You are feeling energy move between you and the world. The surface is telling a quiet story through your skin, even if the exact temperature remains hidden. And as the evening settles, that thought can become restful. The objects around you are not demanding attention. They are simply exchanging warmth, slowly finding balance, and becoming part of the calm background of the room. You can let yourself do the same, releasing the day little by little, until the world feels softer and sleep feels closer. Chapter 6: How the same physics makes stars shine. The light of a star may seem impossibly distant from the warmth of ordinary objects, but the same deep relationship between temperature, matter, and radiation is what allows a star to become visible across space. A star is often described as a burning ball of gas, because that is the easiest image to picture. The comparison works emotionally, but it can mislead scientifically. The candle burns because of a chemical reaction between fuel and oxygen. A star shines because its inner regions are hot, dense, and pressurized enough for nuclear fusion to occur. In the heart of a star like the Sun, hydrogen nuclei are pressed together so intensely that they can combine into helium through a chain of nuclear reactions. In that process, a small amount of mass is transformed into energy. That energy becomes the hidden source behind the light that eventually reaches your eyes. The important point is that fusion creates the energy, while the star's hot matter controls how much of that energy escapes as radiation. The surface of a star is not solid like the surface of a planet. It is a glowing layer of hot plasma, a state of matter in which many atoms are stripped into charged particles. This outer visible layer is called the photosphere. It is the region from which much of the visible light finally escapes into space. The photosphere shines because it is hot, and hot dense matter emits a broad spread of electromagnetic radiation. This is where the earlier physics returns on a much grander scale. Warm objects in a room emit mostly infrared radiation because their temperatures are modest. The surface of a star is vastly hotter, so the radiation shifts toward shorter wavelengths, including visible light. A star does not need a flame in the ordinary chemical sense. Its surface glows because the particles there are moving with tremendous thermal energy, interacting with electromagnetic fields and sending radiation outward. The Sun looks yellow-white from Earth, although its strongest visible output is spread across a range that the human eye and atmosphere interpret in familiar ways. Its surface temperature is high enough that a large portion of its radiation falls in the visible range, which is one reason life on Earth evolved eyes sensitive to that light. The match between sunlight and human vision is not accidental in a mystical sense. It reflects the environment in which life developed. Our eyes became useful because the Sun filled the daytime world with visible radiation that could reveal shapes, movement, distance, and color. Different stars shine with different colors because their surface temperatures differ. Cooler stars tend to appear reddish or orange. Hotter stars can appear white or blue-white. These colors are not decoration, they are information. A red star is not simply painted red by space. Its surface radiation is weighted toward longer visible wavelengths. A blue-white star has a hotter surface, so its radiation includes more shorter wavelength light. By studying color and spectrum, astronomers can estimate stellar temperatures even when the stars are far beyond any possible journey. This connection between color and temperature is one of the great bridges between everyday physics and cosmic science. A heated piece of metal slowly changing from dull red to bright orange shows the same broad rule that helps classify stars. The metal and the star are wildly different in size, structure, and energy source, but both reveal temperature through radiation. The universe gives away its conditions through light. Still, stars are more complicated than simple hot surfaces. Inside them, energy must travel from deep layers to outer layers before it can escape. In a star like the Sun, the energy begins in the core, where fusion occurs. From there, it moves outward through regions where radiation is absorbed, re-emitted, and scattered many times. Farther out, hot material can also carry energy by rising and sinking, somewhat like slow-boiling motion on an enormous scale. By the time energy reaches the visible surface, it has been processed by the star's interior for a very long time. This means the sunlight arriving at Earth has a long history. The energy may begin as a product of nuclear fusion deep in the Sun. It then makes its way outward through dense layers, where a single packet of light can be absorbed and re-emitted repeatedly. Once energy finally escapes the photosphere, it travels through space at the speed of light and reaches Earth after a short journey compared with the vast age of the solar system. The warmth on your skin during the day is the final stage of a process that began in the hidden pressure of a star. Stars also shine because gravity holds them together. Gravity pulls the star's matter inward, creating pressure and temperature in the core. Fusion pushes back indirectly by producing energy that helps support the star against collapse. A stable star is a balance between inward gravity and outward pressure. If that balance changes, the star evolves. It may expand, contract, heat, cool, shed outer layers, or end its life in a compact remnant. The light of a star is therefore not only a glow. It is evidence of a long struggle between gravity and energy. The size of a star matters as well. A large surface can release more total light than a smaller one at the same temperature. A red giant may have a cooler surface than the Sun, yet it can be extremely luminous because its outer layers have expanded to an enormous size. A white dwarf can be very hot at the surface, yet much less luminous than a giant star because it is so small. Brightness then is shaped by temperature and size together. Color tells one part of the story. Total light output tells another. The material in a star also leaves signatures in its light. As radiation passes through the outer layers, atoms and ions absorb or emit particular wavelengths. These patterns can reveal which elements are present. Hydrogen, helium, calcium, sodium, iron, and many other elements can leave recognizable marks. This is how scientists know what stars are made of even from great distances. The star's light carries both its thermal character and its chemical fingerprints. That may be one of the most remarkable ideas in astronomy. A star is too far away to touch, too hot to approach, and too large to hold in any direct human sense. Yet its light arrives carrying information about temperature, motion, composition, magnetic activity, and sometimes even the presence of planets nearby. The glow is not a vague shining. It is a physical message that has crossed space. The sun is the closest and most important example for us. Its radiation warms Earth, powers weather, drives the water cycle, and provides the energy that plants use through photosynthesis. Nearly every meal, breeze, forest, and ocean current is connected in some way to sunlight. Even fossil fuels formed from ancient living matter carry stored energy that originally came from the sun. The star at the center of our solar system is not simply a bright object in the sky. It is the main energy source behind the surface activity of our planet. Yet the sun is also ordinary in the larger family of stars. Across the galaxy, stars are born in cold clouds of gas and dust when gravity gathers material into denser regions. As a forming star contracts, its center heats. If it becomes hot and dense enough, fusion begins and the object enters a long, stable stage of shining. Smaller stars can burn gently for immense spans of time. More massive stars shine fiercely and use their fuel much faster. Their brightness is dramatic, but their lives are shorter. This variety gives the night sky its hidden depth. To the eye, stars may look like tiny white points. Through scientific understanding, each point becomes a physical object with temperature, mass, size, age, chemistry, and future. Some are young and blue-white, burning through fuel quickly. Some are older, cooler, and redder. Some swell into giants. Some shrink into dense remnants. Some exist in pairs, pulling on each other and changing each other's lives. Their light is the outward sign of inner conditions. The same physics also explains why stars eventually change. As fuel in the core is transformed, the balance inside the star shifts. New stages of fusion may begin in some stars. Outer layers may expand. Surface temperatures may change. The color and brightness of the star can evolve over time. A star is not a permanent lamp. It is a long event, shaped by gravity, heat, pressure, and nuclear reactions. This makes starlight feel both familiar and extraordinary. Familiar because it obeys the same broad principles of radiation and temperature that operate in ordinary matter. Extraordinary because the scale is so vast. A warm cup gives off invisible thermal radiation. A star gives off enough radiation to light planets, shape atmospheres, and make life possible across space. The difference is size, temperature, and energy source. Yet the underlying language of matter and light remains connected. So when you see sunlight on a wall or a star through a dark window, you are seeing heat made visible by extreme conditions. You are seeing energy that began in hidden interiors and escaped as radiation. You are seeing matter reveal its state through light. The quiet glow of objects around you and the brilliance of stars are not separate mysteries. They are different expressions of one physical relationship. Temperature gives matter a voice, and radiation carries that voice through space. As this chapter ends, let the thought settle gently. The same universe that makes a star shine also allows warmth to move softly through the room around you. The light from the sky and the quiet heat beside you belong to one continuous story, and for now, you can simply rest inside it. Chapter 7. Seeing the Universe in Infrared. Infrared astronomy changes the universe from a field of distant lights into a hidden landscape of warmth, dust, newborn stars, planets, and ancient galaxies that ordinary eyes could never fully recognize. Visible light gives the night sky its familiar beauty. It shows stars as points, planets as wandering lights, and bright nebulae as faint clouds when the sky is dark enough. For centuries, this was the main window humans had into space. Yet visible light is only one way the universe speaks. Many objects are too cool, too dusty, too faint, or too distant to reveal themselves clearly in the light our eyes can see. Infrared astronomy opens a different window, one that is especially good at finding the quiet, hidden, and partly concealed parts of the cosmos. Infrared light is closely connected to temperature. Objects that are cooler than stars often do not shine strongly in visible light, but they can still release infrared radiation. This makes infrared astronomy powerful for studying planets, moons, asteroids, dust clouds, cool stars, and forming stars still wrapped inside the material that gave birth to them. In visible light, these objects may look dark or nearly invisible. In infrared, they can become bright enough to study. One of the most important roles of infrared astronomy is seeing through cosmic dust. Space is not perfectly empty between the stars. It contains gas, tiny solid grains, and clouds of material spread across galaxies. Dust can block visible light very effectively. In photographs taken with visible light, dust clouds often appear as dark lanes, hiding what lies behind them. Infrared light, with its longer wavelengths, can pass through many dusty regions more easily than visible light. It does not pass through everything, because very dense dust can still block it, but it often reveals structures that visible light cannot reach. This is why star-forming regions look so different in infrared. Stars are born inside large clouds of cold gas and dust. Gravity slowly gathers parts of these clouds into denser knots. As material falls inward, the center heats up and begins forming a young star. During the earliest stages, the newborn object may be buried inside a thick cocoon of dust. Visible light from the young star can be scattered or absorbed before it escapes. Infrared observations can reveal the warm dust around the forming star, the hidden glow of the young object, and the shape of the surrounding cloud. In visible light, a stellar nursery may seem like a dark patch against a brighter background. In infrared, the same region can become a glowing, layered scene, full of knots, filaments, cavities, and young stars at different stages of formation. Dust is no longer only something that blocks the view. It becomes part of the story. It absorbs energy from nearby stars and re-emits that energy as infrared light. The material that once hid the newborn stars begins to announce their presence. Infrared astronomy also helps us study objects that are too cool to shine like stars. Brown dwarfs are an example. They are often described as objects between planets and stars because they form somewhat like stars but do not sustain hydrogen fusion in the same long-lasting way as true stars. Many brown dwarfs are dim in visible light, yet they release infrared radiation because they still hold heat. Infrared instruments can find them and measure their temperatures, atmospheres, and changes over time. Planets also become more accessible in infrared. A planet near a bright star is difficult to see because the star overwhelms it in visible light. In infrared, the contrast can sometimes be more favorable, especially when the planet is warm and radiating its own heat. This does not make planet imaging easy. Stars are still extremely bright, and planets are still small and distant. But infrared observations can help separate planetary signals from stellar glare and can reveal details about temperature, clouds, and atmospheric chemistry. The atmosphere of a planet can leave marks in infrared light. Molecules absorb particular wavelengths linked to their vibrations and rotations. Water vapor, carbon dioxide, methane, and other gases can shape the radiation passing through or coming from an atmosphere. By studying these patterns, scientists can learn what gases may be present around planets beyond the solar system. This is delicate work because the signals are faint and the measurements are difficult. But infrared light gives access to molecular information that is central to understanding distant worlds. Infrared views are also valuable inside our own solar system. The surfaces of asteroids, moons, and planets absorb sunlight and release heat. By observing their infrared emission, scientists can estimate temperatures, surface properties, and sometimes sizes more accurately than visible light alone allows. A dark asteroid may reflect little sunlight, making it difficult to judge its size from brightness in visible light. In infrared, its own thermal glow can provide another way to understand it. The object is still faint, but its heat carries information. Even dust drifting through a planetary system can be studied this way. Tiny grains warmed by a star emit infrared radiation. Around young stars, disks of dust and gas can reveal where planets may be forming. Around older stars, dusty debris can hint at collisions between small bodies, similar to the way asteroids and comets shape our own solar system. Infrared astronomy turns dust from a nuisance into evidence. There is another reason infrared is important. The expansion of the universe stretches light. When light travels across immense cosmic distances, the expansion of space can lengthen its wavelength. Light that began as ultraviolet or visible radiation in a young galaxy can arrive after billions of years shifted into infrared. This means infrared telescopes are essential for studying some of the earliest galaxies we can observe. Looking in infrared is partly a way of looking far back in time because the ancient light has been stretched on its journey. These early galaxies are not nearby objects with simple appearances. They are faint, distant systems seen as they were when the universe was much younger. Infrared instruments help reveal their light after cosmic expansion has moved it beyond the visible range. Through this, astronomers can study how galaxies assembled, how stars formed in the early universe, and how structure emerged from a younger cosmic environment. The same kind of radiation that reveals warm dust nearby also helps uncover light from the deep past. To observe infrared light well, telescopes face special challenges. Warm objects emit infrared radiation, and telescopes themselves are warm unless they are carefully cooled. If an infrared instrument is too warm, it can glow in the very wavelengths it is trying to detect, creating unwanted background signal. This is like trying to listen for a whisper while standing beside a loud machine. For sensitive infrared astronomy, detectors often need to be kept extremely cold. Some observatories are placed in space because Earth's atmosphere absorbs many infrared wavelengths, and because space can provide a colder, clearer observing environment. The atmosphere is both protective and limiting. It shields life from harmful radiation and helps keep Earth habitable, but it also blocks or absorbs large parts of the infrared spectrum. Water vapor and other atmospheric gases are especially important in this absorption. Ground-based infrared astronomy is still possible in certain wavelength ranges, especially from high dry locations where the air contains less water vapor. Space telescopes extend the view further by rising above the atmosphere and reducing interference from Earth's warmth. Infrared images can feel dreamlike because they reveal a universe with different priorities. Visible light often emphasizes hot stars and illuminated surfaces. Infrared can emphasize cooler dust, hidden stars, warm planets, and distant red-shifted galaxies. A familiar galaxy may look sharper in one region and softer in another. Dust lanes that seem dark may glow. Newborn stars may appear inside clouds that looked opaque. The same universe is being seen through a different question. This does not make visible light less important. Visible astronomy remains essential for understanding stars, galaxies, and many physical processes. Infrared adds another layer. Each wavelength range gives a different kind of evidence. The deepest understanding comes from combining them. A star-forming cloud, for example, may need visible observations to show exposed stars, infrared observations to reveal embedded young stars and warm dust, radio observations to map cold gas, and other wavelengths to complete the picture. The universe is too rich for one kind of sight. Infrared astronomy also changes the emotional feeling of space. It shows that the dark places between bright stars are not always empty. Some are full of material preparing to form new stars. Some are dusty regions warmed from within. Some hide planets, disks, and chemical complexity. Darkness in visible light can be a curtain rather than an absence. Behind it, matter may be cooling, gathering, glowing, and changing. This connects back to the room around you in a quiet way. Infrared is the light of warmth, and warmth exists at many scales. It leaves your skin, rises from a stone after sunset, glows from dust around a newborn star, and escapes from planets orbiting other suns. The same broad kind of radiation that makes ordinary objects visible to thermal cameras also lets astronomers study hidden regions of the universe. The difference is scale, distance, and sensitivity. To see the universe in infrared is to accept that reality often hides in wavelengths we cannot naturally perceive. The eye gives us stars. Infrared gives us the places where stars are forming, the dust that builds planetary systems, the faint heat of smaller worlds, and the stretched light of galaxies from the early universe. It does not replace the visible sky, it deepens it. And as you imagine that hidden infrared universe, let it become calm rather than vast and overwhelming. Somewhere beyond sight, cold clouds are glowing softly, dust is warming around newborn stars, and distant galaxies are sending old light across time. The dark is not empty. It is quietly full, and for now you can rest beneath it. Chapter 8. The Afterglow of the Big Bang. The most ancient glow we can observe is not the light of a star, but a faint thermal remnant from the early universe, stretched by cosmic expansion until it now fills space as microwave radiation. This glow is called the cosmic microwave background. The name sounds technical, but the idea is surprisingly gentle. It is the leftover light from a time when the universe was much younger, hotter, denser, and filled with a glowing mixture of particles and radiation. Long before planets, stars, galaxies, dust clouds, or living beings existed, the universe itself was hot enough to shine. Today, that early light is still here. It does not come from one direction. It arrives from everywhere, forming a faint background that surrounds every galaxy and every observer. To understand why this glow exists, it helps to picture the early universe as a place where light could not travel freely for long. The young universe was filled with a dense plasma, a state of matter where electrons were not yet settled into stable atoms. Free electrons were everywhere, and they kept scattering light. A photon, a small packet of electromagnetic radiation, could not simply move across space in a straight line. It would run into charged particles again and again, changing direction repeatedly. The universe was bright, but it was also foggy. Light existed, but it was trapped in constant interaction with matter. As the universe expanded, it cooled. Expansion did not mean that matter was flying outward into empty space from a central point. It means that space itself was stretching, increasing the distance between regions of the universe. As this happened, the hot plasma lost energy. Eventually, the temperature dropped enough for electrons to join with atomic nuclei. Mostly, they formed neutral hydrogen and helium atoms. Once electrons were bound inside atoms, they were no longer freely scattered through space in the same way. The cosmic fog began to clear. This moment happened when the universe was roughly 380,000 years old. Compared with the present age of about 13.8 billion years, that is extremely early. Yet it was already long after the first fraction of a second, long after the earliest particles had formed, and long before the first stars began to shine. It was the time when the universe became transparent to light. The radiation that had been trapped in the plasma could finally travel freely through space. That released light is what we now observe as the cosmic microwave background. It is sometimes described as the afterglow of the Big Bang, but that phrase needs care. The Big Bang was not an explosion into empty space. It was the early, hot, dense state of the universe and the beginning of cosmic expansion, as described by modern cosmology. The background radiation is not light from a single fireball at the center of everything. There is no center in that simple sense. The glow comes from all directions because, in the early universe, every region was hot and filled with radiation. When that ancient light first began traveling freely, it would not have looked like the cold microwave background we measure today. The universe was far hotter then. The radiation had a thermal character, like the glow from hot, dense matter. If human eyes could somehow have existed there safely, the surrounding universe would have been filled with a bright, hot light. But space continued to expand. As light traveled through that expanding space, its wavelengths were stretched. Shorter wavelengths became longer. Energetic radiation became less energetic. This stretching is called cosmological redshift. Over billions of years, that once hot glow was stretched far beyond visible light. Today it appears mostly as microwave radiation. Its temperature is only a few degrees above absolute zero, which means it is extremely cold compared with everyday life. Yet it is still a real thermal glow. It is the cooled remnant of the early universe, a signal that has survived across nearly all of cosmic history. This is one reason the cosmic microwave background is so important. It is the oldest light we can observe directly. We can see galaxies whose light has traveled for billions of years, but the cosmic microwave background comes from an even earlier stage, before stars and galaxies existed. It is like a boundary in ordinary light-based observation. Before that time, the universe was opaque, so photons could not travel freely to carry a clear image. The background marks the moment when the universe first became transparent enough for light to move across space and eventually reach us. The background is also remarkably uniform. No matter where astronomers look in the sky, they find nearly the same faint microwave glow. This uniformity tells us that the early universe was extremely even on large scales. Yet, it was not perfectly smooth. Sensitive instruments detect tiny temperature differences from one direction to another. These variations are small, only subtle ripples in the background glow, but they are profoundly important. They are linked to slight differences in density in the early universe, regions where matter was a little more or less concentrated. Those tiny differences became the seeds of later structure. Gravity slowly amplified them, slightly denser regions pulled in more matter. Over vast stretches of time, this process helped form the first stars, galaxies, clusters of galaxies, and the enormous cosmic web. In that sense, the cosmic microwave background is both an afterglow and a kind of early map. It shows the universe before it had visible structure, while already carrying the patterns that would eventually grow into everything we see. The word map is useful, but it can also mislead if imagined too literally. We are not looking at a flat surface painted on the edge of space. We are receiving ancient light from every direction. Light that last interacted with matter at a particular stage in cosmic history. Because light takes time to travel, looking far away is also looking back. The cosmic microwave background is a spherical view around us of the early transparent universe, not because Earth is central, but because every observer sees their own surrounding shell of ancient light. This idea can feel strange. If there were an observer in a distant galaxy, that observer would also see a cosmic microwave background in every direction. Their view would come from a different surrounding region of the early universe. The background is not an object sitting somewhere far away. It is a relic radiation field filling the observable universe, arriving from the past along every line of sight. The discovery of this background changed cosmology because it provided powerful evidence that the universe was once much hotter and denser than it is now. The universe that had always existed in the same general state would not naturally contain this kind of cooled thermal relic from an early hot phase. The cosmic microwave background fits the picture of an expanding universe that began in a hot, dense condition and has been cooling ever since. It is one of the main reasons modern cosmology treats the Big Bang model as the foundation for understanding cosmic history. There is also a direct connection between this ancient glow and the theme of this video. The background is thermal radiation. It is temperature written into light. Earlier chapters explored how warm objects emit radiation, how stars shine from hot surfaces, and how infrared astronomy reveals hidden warmth in the universe. The cosmic microwave background carries the same broad principle to its greatest scale. It is the temperature history of the universe itself, preserved as light. Of course, the universe today is not uniformly filled with visible fire. It has cooled, expanded, and changed. Galaxies now shine in clusters and filaments. Stars form and die. Planets orbit, dust gathers. Empty-looking regions stretch between cosmic structures. Beneath all of that later complexity, the cosmic microwave background remains as a nearly even glow. It is faint, cold, and invisible to eyes, but it is everywhere. The background also gives scientists a way to measure the universe with extraordinary precision. By studying its tiny variations, they can learn about the universe's age, composition, geometry, and early conditions. The pattern holds clues about ordinary matter, dark energy, and the physics of the early cosmos. It does not answer every question. It does not show the very first instant directly, but it gives a clear, measurable window into a time when the universe was young enough that no star had yet formed. There is something deeply calming in this. The oldest light we can see is not harsh or dramatic today. It is faint, cold, and steady. It has been traveling through expanding space for billions of years, passing through the long ages in which galaxies formed, stars burned, planets cooled, and life eventually appeared on at least one small world. It is older than the Earth, older than the Sun, older than the Milky Way in its present form, and still, in a quiet way, it is here. When you sit in a dark room, surrounded by ordinary objects glowing in wavelengths your eyes cannot see, the universe beyond that room is also filled with a more ancient, invisible glow. The warmth of nearby things and the afterglow of the early cosmos belong to the same larger story of radiation, temperature, and time. One is close and personal. The other is almost unimaginably old. Both remind us that light can remain present even when darkness seems complete. So let this thought become soft at the end of the chapter. All around you and far beyond you, the universe carries its memory as a quiet glow. The day may fade, the room may darken, and your eyes may close, but the story of light continues gently in the background, asking nothing from you now except rest. Chapter 9. Why everything is slowly cooling. Cooling is one of the quiet directions built into the universe, because whenever heat has a path to spread outward, energy tends to move from concentrated warmth into a wider and less concentrated form. You can see this in the simplest objects around you. A cup of tea does not stay hot forever. A stone warmed by sunlight slowly loses its stored heat after evening comes. A room that has been heated will gradually cool if the source of warmth is removed. These changes seem ordinary because they happen every day, but they point toward a deep rule of nature. Heat flows from warmer places toward cooler surroundings until balance is approached. The process can be slowed, redirected, or temporarily reversed in a small region if energy is supplied, but the larger tendency remains. Warmth spreads. This does not mean that every object is cooling at every moment. A kettle can be heated, a planet can absorb sunlight, a body can generate warmth through metabolism, a star can produce energy through nuclear fusion. Local warming happens constantly, but each of these examples depends on an energy source. When the source weakens or when energy is allowed to escape, the stored warmth begins to spread outward again. Cooling is the return of energy from a concentrated state toward a more distributed one. A hot object cools because it loses energy in several ways. It can pass heat into another object by direct contact. It can warm the air or water around it, and that moving material can carry heat away. It can also release energy as electromagnetic radiation. In real situations, these pathways often work together. A hot mug warms the table beneath it, heats the air above it, loses steam from its surface, and emits invisible radiation. The mug is sharing its energy with the surroundings. This sharing is connected to entropy, one of the most important ideas in physics. Entropy is often described as disorder, but that word can be too simple. A better way to think about it here is the spreading of energy among more possible arrangements. Concentrated energy can do useful work because it is unevenly distributed. Heat in a hot engine, sunlight falling on a cool planet, or chemical energy stored in food can drive change because there's a difference, a gradient, between one state and another. As energy spreads out more evenly, there is less available contrast to power motion, chemistry, or organized activity. The cooling of everyday objects is therefore a small example of a larger thermodynamic direction. A warm surface in a cooler room is a temporary imbalance. The surface has more thermal energy than its surroundings. Over time, that imbalance becomes smaller. The object cools, the surroundings warm slightly, and the difference fades. The process feels simple because the scale is familiar. Yet it expresses a rule that applies from kitchen tables to planets and stars. Earth itself is constantly involved in this balance. It receives energy from the sun, and sends energy back into space. If Earth absorbed sunlight without releasing energy, the planet would keep warming. If it released more energy than it received for a long time, it would cool. The climate system depends on the balance between incoming solar radiation and outgoing thermal radiation, shaped by clouds, oceans, ice, land, and atmospheric gases. The planet is continually exchanging energy with space. Deep inside Earth, there is also internal heat. Some of it is leftover energy from the planet's formation, when impacts, compression, and separation of materials created enormous warmth. Some of it comes from radioactive decay inside rocks. This heat drives geological activity over vast timescales, helping power mantle motion, volcanoes, and the slow recycling of the crust. Yet Earth's interior is also cooling overall. The process is extremely slow, and the planet remains geologically active, but the long trend is one of heat gradually leaking away into space. Other worlds tell similar stories in different ways. Small bodies such as asteroids and small moons lose internal heat more quickly because they have less volume compared with their surface area. Large planets can hold heat for much longer. Giant planets still emit more energy than they receive from the sun, showing that they retain internal warmth from formation and ongoing processes. A world's size, composition, atmosphere, and distance from its star all shape how quickly it cools. Temperature becomes a history of energy gained, stored, moved, and lost. Stars seem to resist this trend because they shine for so long, but they too are part of the same larger story. A star remains bright while it has fuel and internal pressure conditions that allow fusion to continue. Fusion releases energy that supports the star against gravity and sends radiation outward. But fuel is finite. A star like the Sun can shine steadily for billions of years, yet it is still changing. Hydrogen in the core is being transformed. The balance inside the star slowly evolves. Eventually, the star will leave its stable stage and move through later phases of its life. Massive stars live far more intensely. They burn through their fuel quickly and end in dramatic transformations. Smaller stars can glow faintly for much longer. But no star shines forever in the same way. Stellar light is the release of stored and generated energy across time. Each star is a temporary island of heat in a universe where energy continues to spread outward. When stars die, their remnants also cool. A white dwarf is the hot, dense core left behind by a star like the Sun after it has shed its outer layers. It no longer produces energy through ordinary hydrogen fusion. It shines mainly because it is still hot, slowly radiating its remaining heat into space. Over immense spans of time, white dwarfs are expected to become colder and dimmer. The process is so slow that the universe is not yet old enough for the coldest final versions to exist, but the direction is clear. Without a lasting internal energy source, even dense stellar remnants fade. Neutron stars also begin extremely hot after their birth in supernova explosions, then cool through radiation and other processes. Black holes are stranger because their temperature and radiation involve quantum effects near the event horizon. For ordinary stellar mass black holes, this radiation is extremely faint in the present universe. Over unimaginable durations, if no new material falls in, black holes are expected to lose energy slowly. Even the most enduring objects are not completely outside the logic of thermal change. On the largest scale, the universe as a whole has cooled as it has expanded. In the early universe, matter and radiation were compressed into a hotter, denser state. Expansion stretched radiation to longer wavelengths, and lowered the average temperature of the cosmic background. The universe today is far colder and more structured than it was in its youth. Galaxies, stars, planets, and living systems have formed inside that cooling history, using differences in temperature, density, and energy to create complexity. This may sound bleak at first, but cooling is also what makes structure possible. If the early universe had remained too hot, atoms could not have formed in a stable way. If gas clouds could not cool, they could not collapse efficiently into stars. If planets could not shed heat, they could not develop stable surfaces. Cooling allows transitions. It lets matter settle into new forms. It permits chemistry, geology, atmospheres, oceans, and eventually biology. Life itself depends on energy flow. Living things maintain order inside themselves by taking in usable energy and releasing waste heat. A living body is a system through which energy moves. Food, oxygen, sunlight, and chemistry create local organization, while heat is released into the surroundings. Life does not violate thermodynamics. It exists because energy gradients are available and because living systems can use them for a time. This is why the universe can contain both cooling and creation. Stars form while gas clouds lose heat. Planets become habitable while they radiate energy into space. Organisms build cells, thoughts, and movement while releasing warmth. Order can appear locally because energy is flowing from concentrated sources toward broader surroundings. The long cosmic trend and the small living moment are part of the same physical picture. The future depends on how energy sources change. Stars will continue forming as long as galaxies contain enough cold gas to make them. Over time, that supply is expected to decline. Existing stars will age. Bright star formation will fade. The universe will become darker as fewer new stars are born and old stars exhaust their fuel. The details involve many uncertainties, but the broad direction in standard cosmology is toward a colder, dimmer future, where usable energy becomes more thinly spread. This does not make the present moment less meaningful. In a cooling universe, warmth is precious because it is temporary. Starlight matters because it does not last forever. Planetary surfaces, oceans, weather, forests, cities, and human lives exist within a rare era when energy gradients are abundant enough to support rich structure. The slow cooling of everything is a reason to notice how remarkable the present warmth is. Every object around you participates in this story. A lamp warms and cools. A wall stores and releases heat. A blanket slows the escape of warmth. A cup cools toward the room. Your body gives heat to the air and surfaces nearby. Far beyond the room, planets glow faintly. Stars spend their fuel, and space itself carries the cooled memory of an earlier, hotter cosmos. The scales are different, but the direction is related. Energy moves, spreads, and slowly becomes less concentrated. And as night deepens, this can become a restful idea. You do not need to hold back the cooling of the day. You can let warmth soften, let thoughts settle, and let the room find its quiet balance around you. For now, there is still warmth here, still breath, still gentle light beyond what the eyes can see, and that is enough. Chapter 10. A universe that glows until it fades. A universe that glows is a universe still spending its energy, and the story of that glow leads from the warmth of ordinary matter to the far future, when light itself may become rare and thin. Everything explored in this video has pointed toward one idea. Matter reveals its temperature through radiation. A body gives off infrared light. A wall quietly exchanges heat with the room. A star turns deep internal energy into visible brilliance. Ancient radiation from the young universe still fills space as a faint, cooled background. Across all these scales, light is more than brightness. It is energy in motion. It is the way warm things communicate with the rest of reality. The universe today is still full of glow. Stars shine in galaxies. Dust absorbs starlight and re-emits it in longer wavelengths. Planets release heat absorbed from their stars and heat left over from their own formation. Gas clouds radiate as they cool, collapse, and form new generations of stars. Even objects that appear dark can carry hidden warmth. Space is not a simple black emptiness. It is threaded with radiation from matter at many temperatures, from the fierce light of blue-white stars to the quiet infrared of cold dust. Yet this glow is tied to imbalance. Something must be warmer than something else. Energy must be concentrated enough to flow, to shine, to drive change. A star shines because its interior is hot and active. A planet radiates because it has absorbed energy or stored heat. A body glows in infrared because metabolism keeps it warm. Wherever there is a useful difference in temperature or energy, radiation becomes part of the movement toward balance. Over time, the universe has been moving from a hotter, denser past toward a colder, more spread out future. This does not mean that nothing new can happen. Stars are still forming, galaxies still evolve, planets still orbit. Life can still use energy in local places where conditions allow. But on the largest scale, the trend is toward expansion, dilution, and cooling. Energy becomes less concentrated. Matter becomes more widely separated. The brilliant activity of the cosmos becomes harder to sustain. The present age is sometimes called the era of stars, because stars are the most obvious engines of light. They gather matter through gravity, ignite fusion in their cores, and release energy into surrounding space. Their glow shapes galaxies and makes planets warm enough for chemistry. But stars require fuel, mostly hydrogen in forms that can gather into dense clouds and eventually collapse. That fuel is not used all at once, and many small stars can live for immensely long times. Still, star formation cannot continue at its current richness forever if the available cold gas is gradually locked away, heated, scattered, or transformed. In the very distant future, the birth of new stars is expected to slow and eventually fade. The exact details depend on cosmic evolution, dark energy, galaxy interactions, and the supply of gas. But the broad picture is that the universe will not always be filled with active star formation. Existing stars will age. Massive stars will vanish first because they spend their fuel quickly. Smaller stars will last much longer, glowing faintly through spans of time far beyond human history. Eventually, even the longest-lived stars will exhaust the fuel that lets them shine. When that happens, the universe will not become empty immediately. It will be filled with remnants, white dwarfs, neutron stars, black holes, planets, brown dwarfs, and cold fragments of matter may remain. Some of these objects will still carry heat. A white dwarf, for example, can glow for an extremely long time simply because it began very hot and cools slowly. But without a continuing source of fusion, it must fade. Its light becomes weaker as its stored thermal energy escapes into space. This future fading is a continuation of the same physics already present in a cooling cup, a warm stone after sunset, or a room after the heat is turned off. The scale is different, but the direction is familiar. Stored heat leaks away. Radiation carries energy outward. Differences become smaller. In the far future, many objects may still exist, but fewer of them will shine brightly. The universe becomes less like a sky full of lamps and more like a dark field of cooling embers. Black holes add a stranger and more uncertain-looking chapter to this story, although the physics behind it is taken seriously. In classical thinking, a black hole is a place from which light cannot escape once it crosses the event horizon. But when quantum effects are considered near that boundary, black holes are expected to have a kind of temperature and to emit extremely faint radiation. For large black holes, this radiation is so weak that it is far beyond anything we can observe directly today. Over staggering durations, if no new matter falls in, black holes are expected to lose energy gradually. This means even the darkest objects may not be absolutely permanent. They may evaporate slowly through a process that belongs to the deep meeting point between gravity, quantum physics, and thermodynamics. The timescales are so enormous that they almost lose ordinary meaning. Long after ordinary stars have ended, black holes may be among the last major objects still present. If they eventually fade too, the universe enters an even quieter state. The idea often called heat death or the big freeze describes this broad future. It does not mean a dramatic explosion or a sudden ending. It means a universe where usable energy has become so spread out that little organized change can continue. Temperatures drift toward uniformity. Bright sources disappear. Differences that once powered stars, weather, chemistry, and life become rarer. The universe does not break like glass. It settles, slowly and almost beyond imagination. There is uncertainty in this picture. The future depends on the nature of dark energy, the long-term behavior of cosmic expansion, the stability of matter, and physical processes that are not fully understood. Some models imagine different endings. The universe could behave in ways current science has not yet revealed. But based on the evidence available today, continued expansion and gradual cooling remain among the most widely discussed possibilities for the long-term cosmic future. It is important to say this without turning it into fear. The fading universe is not a threat waiting nearby. The times involved are immense beyond daily experience. Stars will continue to shine for ages far longer than human civilization has existed. The sun itself has a long future ahead, though not an infinite one. Galaxies will continue their slow gravitational dance. New stars will still form from clouds of gas for a very long time. The fading is real as a direction, but it is gentle on cosmic scales. This final chapter is less about doom than perspective. The glow around us matters because it is temporary. The fact that energy can still gather into stars, planets, weather, oceans, cells, and thoughts is extraordinary. We live in an age when the universe is old enough to contain heavy elements, rocky worlds, and complex chemistry, yet young enough that stars still fill the dark with light. We exist in a warm interval between a hotter beginning and a colder future. Every visible thing is part of that interval. A candle flame, a lamp, a warm hand, a star in the night sky, and a distant galaxy all belong to the same story of energy being released. Some glow brightly, some glow invisibly, some glow only through instruments that translate hidden wavelengths into images. The universe is not dark because it has nothing to say. It is dark because much of its message lies outside the narrow range of human sight. In the end, the phrase, "every object around you is glowing," becomes more than a curiosity. It becomes a reminder that existence is active. Matter is never merely sitting in silence. It carries energy, exchanges energy, and leaves traces in radiation. Even stillness has a hidden motion. Even darkness has a background. Even the quietest object belongs to the long thermal history of the cosmos. One day in the far future, the grand lights may fade, the stars may end their burning, the remnants may cool, and the last sources of concentrated energy may become thin and distant. But that future only makes the present glow more meaningful. Right now, the universe is still luminous. It still builds stars from clouds, warms planets with sunlight, and allows small living bodies to radiate gently into their rooms at night. So as this journey closes, imagine the darkness around you with kindness. It is not empty. It is filled with soft exchanges of heat, with ancient radiation, with starlight traveling across space, and with the quiet warmth of your own body. The universe glows until it fades, and for this moment, you are part of its glow. Let that thought be enough. Let the day loosen. Let the room become still, and let yourself drift gently into rest. And now, my friend, we've reached the end of this quiet journey through invisible light. Every object around you is still glowing softly. Your room, your body, the earth beneath you, the stars beyond you, and even the oldest light in the universe all belong to the same gentle story of warmth, radiation, and time. If you're still awake and would like to keep drifting through science, you can choose another video and let the next journey begin softly from here. But if sleep is already close, let the day fade now. Let the room become quiet. Let the hidden glow of the universe continue without needing anything from you. Sweet dreams among the stars,